This is problem HRW96P010 on WebAssign. So we've got this box on a floor. It says it's initially stationary of mass m on a floor. When we apply a force of some multiplier times mg right here at an upward angle of, well, an angle. Okay, so first off, what is the magnitude of the acceleration of the block across the floor if mu s equals 0.6 and mu k equals 0.5, and then we ask it again, but we change the mu's. Okay, whenever they ask you something like this, the first thing you've got to check is if you're even going to break the static friction. So let's do a free body diagram of this this block. Okay, here's our block. We've got a force F. Come on. Okay. Well, I'll leave that off for now. We've got that force is at an angle, theta, and I've got the weight of the block will be pointing down. Okay, and we have a normal force. And we have friction. And it's going to be in the opposite direction of the motion or possible motion. If this thing's going to move, it's going to move to the right, so friction must be over here. Okie dokie. Well, I need to check. I need to find out what the maximum static friction is. But to do that, I need the normal force. So let's find the net force in the y direction first, so we can figure out what the normal force is. So the net force in the y direction is going to be 0 because this thing is going to stay on the ground. Sorry, my throat is all franky. So net force in the y direction, I've got the normal force pointing up. I also have the y component of F, so that'll be F sine theta, and I've got mg pointing down, and that all equals 0. So basically the normal force is going to be, let's see, move that over there, mg minus F sine theta. Okay, excuse me. Well, F, back over here, F is actually a number times mg. So let's put that in there. So I've got mg minus 0.530, 0.530 mg, and then I've got my sine theta on there. Okay, look, I can pull this mg out. So let's do that. Just pull that mg out. So n is going to be mg times 1 minus 0.53 sine, and I'm going to go ahead and put theta in. My theta is 17 degrees. Okay, so in the end, my normal force is mg times, we need to do that in the calculator, and I get 0.845. Okay, so I have to open this up more. So that means that if mu s is 0.6, I'm going to make this full screen. Mu 6 is 0.6. Change colors here. Okay. So mu s is 0.6. And the normal force is all of this. That means that the maximum static friction is mu times the normal force, which in this case is 0.6 times 0.845 times mg, which I get 0.51. I'm gonna round it. 0.51 mg. Okay, now that is the maximum friction I can have. Let's see if the force I'm pulling with is enough to break that. By the way, this is in newtons. Well, in the x direction, I've got the x component of the force So that's going to be F cosine theta. So the force I'm actually pulling with, see if it breaks this or not, is 0.53 mg cosine of 17 degrees. Pop that in the calculator. Okay, and I get 0.506 mg. I actually have to go back and look at this. This was 0.507. Oh, this got really close. Hopefully your numbers won't be quite that close, but this was actually 0.507 when I rounded up. So the friction, the maximum static friction force, is more than the force that I'm pulling in the next direction. So this thing actually, I'm not going to break the static force, the static friction force. So the acceleration under these circumstances will be 0 because I didn't break the friction. And that's what I get. So the acceleration is 0. Now what if we change it again? If we change it so that mu s is 0.4, in that case, the maximum, so this is part B, in that case, the maximum static friction is 0.4 times 0.845 mg, okay, which is 0.338, okay. Fx is definitely enough to break that. So we're going to break that, and we're going to move into kinetic friction. So the kinetic friction is going to be, what was it, 0.3 times the normal force, which is 0.2535 newtons. Okay, so what I've got going on now is going back to the free body diagram. Once I've broken the static friction, this thing is moving along. The friction over here is going to be 0.2535 mg, by the way. Oh, I keep forgetting the mg's. I'm sorry. mg. Okay. So, that means that the net force in the x direction, net force in the x direction is going to equal mass times acceleration. The net force in the x direction is, well, I'm pulling with F cosine theta. That was what we did up here. We had 0.506 mg. Okay, so 0.506 mg minus the frictions to the left-hand side, so that's 0.2535 mg. Okay, that's going to equal mass times acceleration. Notice I've got mass in all of them, so I'm going to get rid of them. There's a mass in every term. Get rid of that. So A equals 0.506 times g minus 0.2535 times g. If I throw all of that in the calculator, I'm going to get the acceleration, which for my numbers ends up being 2.4745. At this point, I can start rounding, so meters per second squared. That is A. Let's go check that. 2.47. Oh, I got 2.48. So I guess I was off by a little tiny bit somehow. Probably because I rounded here. I rounded up here a little bit. Okay. So that is the end of that problem. Remember, you have different numbers, but it's the same general idea.